Well, this overall unit of study on two-dimensional motion is really comprised of three major areas of emphasis. Now, the first one we've covered, that was everything we went over regarding projectile motion. So half parabolic trajectories, full parabolic trajectories, and other cases like launching a projectile up a steady incline, for example. And we also investigated centripetal acceleration and how that relates to uniform circular motion. So the last area of emphasis is on what we call relative velocity. So let me attempt to clarify what I mean by relative velocity. So the classic example would be something like, what if you were standing in the back of a pickup truck and the truck has a velocity or speed, no, velocity, right? Because I'm showing the direction as well. I'm representing it as a vector. And the car is perhaps going 30 meters per second down the freeway. And, well, I don't recommend you stand in the back of a pickup truck on the freeway, but this is, after all, just a thought experiment. And then you take a baseball and you throw it forward with a velocity equal to about, I don't know, maybe 10 meters per second. Then how fast does the baseball appear to be going to this person who's just standing here on the side of the road? So really, I was a bit vague about the way I expressed these velocities. I guess I should say that this velocity, here I'll put some subscripts. This is a velocity subscript TG. What I mean is it's the velocity of the truck with respect to the ground. So let me put some labels here. Truck, G, ground, and then one more, we'll put B, ball. So when I say 10 meters per second, I mean what's the velocity of the ball with respect to what? With respect to the truck. So we have here are really two frames of reference. In fact, I encourage you to try to find a YouTube video. If I come across it, I'll provide a link as well. I've seen it before, and I believe it was on YouTube, and I'm pretty sure the one I'm talking about is just called Frames of Reference. This very old black and white video from, goodness, I think it's from the 1950s, that give a perspective of moving objects from two different points of view, from two different frames of reference. And it really does a good job of illustrating and highlighting what we're getting at in this video lesson. Anyway, if I just carry on with this thought experiment, the velocity of the ball with respect to the truck is 10 meters per second. So when we say, what does this guy describe the motion of the ball as? What we mean is, what's the velocity of the ball, not with respect to the truck, but what's the velocity of the ball with respect to the ground? So what we're applying here is something known as the Galilean Transformation, and it goes something like this. I'm going to state an equation in general. The Galilean Transformation tells us the velocity of object A with respect to reference frame C is equal to the velocity of that object A with respect to reference frame B plus the speed of reference frame B with respect to reference frame C. That's sort of a lot to take in, right? Well, the way I look at it, it's as if you state this equation correctly, the linking frame of reference that's sort of in the middle of this equation goes away. So, well, that's not really a good conceptual explanation. Let's just see if we can apply it specifically to this case. So we should be able to say that the velocity of the ball with respect to the ground is the velocity of the ball with respect to the truck plus the velocity of the truck with respect to the ground. So these are velocities. I'm putting the symbol above the V in each case. And I think that makes sense. I think just on a gut check level, you would probably say, just naturally you get it, this guy's going to say it's moving at 40 meters per second. And indeed, that's exactly it, right? 10 meters per second combined with the truck's 30 meters per second gives us a value of 40 meters per second. So no surprise here. The Galilean transformation is actually pretty gosh darn intuitive. Now, it leads to some challenging questions, and perhaps the most famous challenge to the Galilean transformation goes something like this. What if you have a high-speed train that's traveling at, how about 80% the speed of light? When we say speed of light, such a special value in physics, we give a symbol for it, lowercase c. Okay, so the train is traveling at 80% the speed of light, and then you turn on the headlight, and that light blasts forward at the speed of light. Then what does a person landlocked say is the speed of the light coming from the headlight? Now, if you apply the Galilean transformation, you would conclude that the speed of light relative to the ground is equal to 180% the speed of light relative to the train. But you're probably familiar with this idea that nothing can travel greater than the speed of light. So it turns out that an observer aboard the train and an observer on the ground would both determine that the speed of light in any case is 3 times 10 to the 8th meters per second. So how could this be? How could two people both give the same measurement? Well, it turns out that the Galilean transformation is only valid for things that go with things that travel with speeds that are very small in comparison to the speed of light. For objects that move at, let's say, a good threshold cutoff would be anything that's moving at greater than about 10% the speed of light has to be treated using what's known as the Lorentz Transformation. And we won't get into the Lorentz Transformation now. We'll save that for the third semester of this course in Physics 4C. All right. There's another question. I can remember specifically when I was in high school, so there's yours truly. I believe that was my senior yearbook photo. And in my senior year, might have been my junior year of high school, was my first exposure to a physics course. And I specifically remember having an argument with one of my classmates about this TV show Knight Rider. And I don't know if you've heard of this or not. This is pretty old. It stars David Hasselhoff. And at the end of several episodes, Knight Rider, David Hasselhoff's character, would drive this old Pontiac into the back of a moving pickup truck. So there was the speed of the car with respect to the truck, there was the speed of the truck with respect to the ground, and there was the speed of the car with respect to the ground. So the truck and the ground both represent two different frames of reference, and we want to be able to figure out what's the speed of the car in both of those reference frames. So how could you use the Galilean transformation to come up with an equation that relates these three velocities? So I'll give you a moment to try to state the equation correctly. Okay, did you get it right? You should say that the speed of the car with respect to the ground is equal to the speed of the car with respect to the truck plus the speed of the truck with respect to the ground. And so I think it went something like this. Let's say the truck was going 60 miles per hour, and then the car was going 61 miles per hour, and then a ramp would come down, and the car would proceed up the ramp, drive into the back of this truck, the latch would close, and then they'd drive off into the sunset, and no one ever knew where the mysterious Knight Rider escaped to. Is this possible? Or was this just TV magic? Would you be able to do this? Because after all, if your car's going 61 miles per hour and you enter the back of this truck, I don't think there's enough safe distance here to slow down from 61 miles per hour to 0 miles per hour without crashing through the back of the truck. And that was my classmate's argument. He said, there's no way this is possible. I think I intuitively understood this idea of relative velocity. In my mind, I said, yeah, the car's going 61 miles per hour relative to the ground, but relative to the truck, the car's only going 1 mile per hour. And so it should very easily be able to slow down once it enters. Now, I'm not going to get into the details of this one. I'll let you try to debate with somebody else whether or not this would be possible. It turns out there's a Mythbusters episode. I don't know if you ever watched that. Even Mythbusters is a fairly old show. Knight Rider is an old enough show. Mythbusters goes back a while too, but perhaps you've seen it. And I am going to link the Mythbusters video in which they've attempted to recreate this problem. So check that out in the next video segment and see what you think. Thanks for